Okay, now in my last video, I did explain why it's true that if a matrix is nilpotent, all the eigenvalues are zero. And the easiest way to see that is that if you had a non-zero eigenvalue, then that eigenvector would always give a non-zero result no matter what power of t you apply to that vector, right? So if, for instance, if the eigenvector has eigenvalue 1/2, right? And I take t to the 5th times that eigenvector, then the result would be 1/32 times the eigenvector. It would not be 0. Okay, so there's no way to get a nilpotent matrix if there's an eigenvalue that's not 0. Now, what's more difficult is to show that if the only eigenvalue is 0, the matrix is nilpotent. And I'm going to outline a proof here. If this is you can kind of skip this over if it's too much, but I think it's good to hear, and maybe if you listen a few times, it will make more sense. Okay, all right. Now, first of all, it's kind of an inductive proof. You're kind of reducing the size of the matrix as you go. So suppose you have a transformation whose only eigenvalue is 0. Now, if the eigenvalue is 0, that means it's singular, right? Okay, so if it's singular, right, because the determinant is equal to 0. So if it's singular, there must be one homogeneous solution vector, which is an eigenvector z of eigenvalue 0. So I'll just take at least one homogeneous solution vector. So this is one non-zero homogeneous vector, solution vector. Okay, so let's write the vector space V as Z plus V prime, where V prime is a subspace of dimension n-1. Okay, consider the transformation T restricted to the subspace V prime. Okay, so I can. There's more than one way to do this, but I can do this in a certain way. I can choose a basis that includes Z and other basis vectors. So for every V prime and V prime, I have TV prime equals W prime plus V, where W prime and V are uniquely determined, right? Okay. Sorry, let me fix this up a little bit. This is not what I meant. What I mean here is that TV prime is going to be in the vector space V, so it's going to be some multiple of Z plus some W prime, okay? So I would say K is uniquely determined and W prime is uniquely determined. But K, W prime, and here note that W prime is in V prime. Okay, and this is direct sum, so I should write this as O plus. So it has dimension n-1, so let's write that. This is the direct sum of these sets, of these vector spaces. So the intersection is going to be empty. All right, but that gives me the entire vector space. All right, so now I have this, and this should be a small v prime, not a big v prime. Right, so any vector v prime in this subspace, it will have some part in Z and some part in W prime. But I can just consider the W prime, and that's going to give me a linear transformation, okay, from V prime to V prime, right, because W prime is in V prime. Okay, so T prime has no non-zero eigenvalues, because T has no non-zero eigenvalues. Now, I'm making a little fudge here, but that you'd have to fill in. But you can believe that T prime is basically T restricted to a subspace. And if T restricted to a subspace had a non-zero eigenvalue, then T would have a non-zero eigenvalue. So the only eigenvalue of T prime is 0. So T prime is singular, so it has at least one eigenvector with eigenvalue 0. So you just continue this way, and you'll keep getting more and more transformations with n non-zero eigenvectors, which are linearly independent. Okay, it's linearly independent because at each stage I'm breaking the set up into a direct sum. Okay, so any vector in the subspace is not in the previous spaces. Okay. So you can verify that if you apply t to the n on all of these vectors here, all these basis vectors, you will get 0. So since t to the n applied to any basis vector is 0, t to the n applied to any linear combination of the basis vectors is also 0. So these are n linearly independent vectors in an n-dimensional basis, in an n-dimensional vector space, so they form a basis. It follows that t to the n is 0 for any vector in V, so t is nilpotent. So this idea of repeated breaking up your space into subspaces and looking at how the transformation acts on subspaces, this is an important idea. And this corresponds to breaking up a matrix into block form, because you're just looking at how the matrix acts on part of the basis and not on the entire basis, right? So if that went over your head, don't worry. Just again, take away the important idea here that if you have a transformation that has only eigenvalue 0, it's a nilpotent transformation. Okay? If there's no non-zero eigenvalues, it's a nilpotent matrix. All right, now so far we've been dealing with matrices that have eigenvalue 0. Now here's where we make the jump. Let's look at non-zero eigenvalues. Let's consider a matrix T that has just one eigenvalue, lambda. Okay, and so let's say lambda is not 0. Okay. Now we've seen cases where matrices have a single eigenvalue that are not diagonalizable. So T is not necessarily diagonalizable. However, T minus lambda I has only eigenvalue 0. Now, why is that? Well, suppose we had T minus lambda I, and suppose it had an eigenvalue that's different, like mu v, like that. That would be, now I can move the lambda I to the other side. That's the same thing as saying that TV equals lambda plus mu of v. Okay. But I said T has only one eigenvalue, lambda. So that means that lambda plus mu equals lambda. So that means that mu equals 0. Okay. So the only eigenvalue of this matrix T minus lambda I is 0. Neat trick. I can add something to the diagonal of a matrix and change its eigenvalue at will. Okay. Another very key trick here. Right. Now, since this only has the eigenvalue 0, we know it's nilpotent, and we know it's similar to block subdiagonal matrix. So very powerful conclusions we've drawn here for a matrix with a single eigenvalue. So what does that give us? So that gives us that P times T minus lambda I times P inverse is similar to a block subdiagonal matrix, which I'll call D prime or something like that. Now, let's see what we can do here. So that means that PT inverse, PTP inverse, I can bring the lambda I to the other side, right? So that's equal to D prime plus P times lambda I times P inverse, okay? Which is equal to D prime plus lambda I, okay? So that's how I get this. D is similar to a block subdiagonal matrix plus lambda I, okay? So the block looks something like this. I have lambdas on the diagonal, and then I have ones on the subdiagonal, okay? Now, I may have several blocks like this, but each block is going to look like this, some diagonal ones and lambdas on the diagonal. Okay? Now, that's for a single eigenvalue. Suppose we do multiple eigenvalues now. Okay, so this is the last step. This is giving me the general case. Of course, any matrix is going to have multiple eigenvalues. Now, I'm basically just going to do a top-level overview of what is going on here because the details get a little bit involved. We've seen before that we have these chains of subspaces when we apply a matrix to itself several times. Now, T is not nilpotent, but we've seen that any matrix has a chain of subspaces that terminates. Okay, the range terminates, and where it terminates is R infinity, and the null space terminates is N infinity. Okay, so I'm going to take this matrix T minus lambda 1I. Now, this is not going to be nilpotent because there are other eigenvalues as well, but it will have a chain of subspaces, and I'm going to take N infinity of this matrix. Okay, and then I'm going to do that for all of the eigenvalues, and I'm going to state this without proof that in fact the vector space is the direct sum of all of these null spaces. Basically, I can break the vector space up into these different null spaces and consider the null spaces separately. It also turns out that T keeps each of these spaces separate. T acts on vectors in this subspace and moves them to vectors in the same subspace. Now there's a little bit of a technical detail to show that. It's first you could see that t minus, for instance, t minus lambda 1I maps the n infinity of t minus lambda 1I to itself. And then from that you can get that t maps n infinity of t minus lambda 1I to itself. So a little bit of a technical detail, but it is true that t separates these different subspaces. Okay. So furthermore, t minus lambda j restricted to this subspace is nilpotent. And that actually follows from the definition of n infinity. Right? It just means that any vector in here, when you keep applying t minus lambda j to it, you end up with 0. Okay? So basically what we want to do is use our single eigenvalue result on each one of these subspaces. Right? So on each one of these subspaces, I can write the matrix as similar to one of these block subdiagonals with lambda on the diagonal. All right? So that means that t can be broken up into blocks, where each block represents the action of t on one of these subspaces. As I said, the different subspaces stay separate, so they basically correspond to different blocks on a block diagonal matrix. Okay. Now, by applying the argument for the single eigenvalue case on each of these subspaces, we get that result, that the block has this form. Okay. So this finally gives us the Jordan form, which I can write out something like this. Get some more space here. And let's get some blocks here. So we've got this matrix form, and we have several blocks. So make lambda 1 be the first block. This has 1s on the subdiagonal and 0s everywhere else. So that's my first block. And of course, these are all going to be 0s down here, and these are all going to be 0s over here. Okay. The next block could be the same lambda. I'll just make it lambda 2. It could be, you could have multiple blocks with the same lambda, but I'll just, like I said, I'll just make it this way. And then these are 0s. And then you keep going down, and the last block is going to look like lambda k, 1, 1, 0, 0. All right. Now, let's consider this matrix t minus lambda 1I dot 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 t minus lambda ki. Okay, so by the way, I can say t is equal to p, and let me just call this, I'll just call it d prime. We have this. Okay. All right. So from the Jordan form, we can see that this matrix is nilpotent. So how does that work? So this if I look at d prime, suppose I apply d prime to the vector 0 dot 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 1. Okay, suppose I do that. Right. Well, what's going to happen? Well, this last matrix here, t minus, so I'll just write this, t minus lambda 1I dot dot dot, and all the way up to t. Now the last matrix I'm going to write out, it's going to have a bunch of stuff up here. Now what about the last block? The last block is going to have 0s on the diagonal like this, right? Because the lambda k is zeroing out this lambda k. Okay. So I'm multiplying all these matrices times this vector 0, 1, and I get 0. All right. Now, suppose I did something a little bit, suppose I did, instead of that, suppose I took d prime squared of 0 dot 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 1, 0. Okay. All right. So I'm applying this matrix. Now, what does this matrix do to this vector 0 dot 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 1, 0? Well, it moves it down to the last place. Okay. Right. Now, this other stuff, these other matrices do some stuff, but it's not going to move the it's not going to move this value from here because this only applies to itself. So it's not going to be 1. It's going to be some constant. I'll call it c. Okay, but d prime applied to this vector is going to be 0. Okay. So similarly, I could do a similar argument to show that d prime that if I take any basis vector and apply d prime multiple times to it, I'll end up with 0. Okay. So I can say a similar argument. Shows that d prime to some power, I can say d prime to the k, or d prime to the n, applied to any basis vector. I just say ej is equal to 0 for any element, any basis vector. Okay, so that's telling me that d prime is nilpotent, and t is similar to d prime, so t is also nilpotent. Okay, so since this is nilpotent, we know that the degree of nilpotency is less than or equal to the dimension of the space. So I know that this product here, t minus lambda 1 I to the n times t minus lambda k I to the n is equal to 0. Okay, because the degree of nilpotency of this matrix is less than or equal to n. Now I'm using the fact that these factors commute, right? T commutes with t, so I can rearrange these factors however I want. Okay, so we can do better than this. We don't have to raise each block to the nth power. Okay, in fact, if you remember, the characteristic polynomial of t has a similar form. These lambdas are the eigenvalues of your matrix T, of the matrix T. So the characteristic polynomial, when factored, has this form. And it turns out that instead of having to raise these factors to n, you just need to raise the factors to a smaller number, which is the number that appears in the characteristic polynomial. Okay, all right. So there's another definition. The minimal polynomial. How did that happen? Okay. Okay, is the smallest. Okay, is the polynomial of the form. All right, now it's going to have the same form, but these exponents are different. They may not be the same exponents as in the characteristic polynomial. So let me use a different letter if I can. If it's going to let me. I'll say L. Okay, and that's L1 up to Lm, Lk. Okay. So let me call this P of x. Okay. Such that P of t is equal to 0. So instead of putting a number in there, I plug the matrix T in there. And this, okay, where these factors Lk or Lj are minimal. Okay, all right. Now, well, it turns out that Lj must be less than or equal to Mj. All right, so that's so Lj is less than or equal to Mj. Okay. All right, so that's kind of a theoretical thing, but the nice thing out of this whole section is the fact that we can write any matrix as similar to this Jordan form here. That's not diagonal, but it's very close to diagonal. Okay, so you can imagine that in general, finding the Jordan form of a matrix is quite complicated. But in fact, it sort of follows this procedure. You can find these null spaces. First, you find the eigenvalues, then you find the null spaces. and then you can work backwards to extract these blocks. So that's one way to do it. But anyway, this gives insight into how or why any matrix is similar to a matrix that looks like this. It may not be diagonal, but it's very close to diagonal. All right, thanks for watching.